Talking about today, we are talking about multiple topics today, but the big topic we are introducing formally today is generics. Generics is all over iOS, right? Generics is one, if not the biggest part of being a competent iOS developer, knowing how to use it, knowing the uses of it. So generics is huge, right? So as I said before, please bookmark this page and please read it in your downtime. Go over it, especially the introductory parts of generics here, which we'll get into some concepts today. So the Apple guide says, generic code enables us to write flexible, reusable functions and types that can work with any type subject to requirements on that type. Right? What does that mean? Back in Unit 1, we used arrays, right? An array is a generic type. Why is an array a generic type? Because in an array, you could have any type you want, right? You could have an array of mixed types, but this is not what we do as Swift developers, because as Swift developers, we don't want to put any type in an array. So we start an array, we say we only want strings in that array, right? But your array could also have integers, right? So a generic, by definition, allows us to work with any type. My array could work with any type, right? Apple goes on to say, subject, this is important here, subject to requirements that you define. What does that mean? So, with a dictionary is a generic type. Do we agree? I could put anything in my dictionary. But what is the one restriction on a dictionary? Anybody? Yes, Christian?
The first is only the index. Okay, again, index is like a key, but not a value.
Right, so there's a key and there's a value, but what is that restriction? Yes, Jahid? It needs to be hashable. The one requirement here in that definition on a dictionary, the key needs to be hashable. In order for the key to be unique, the key needs to be hashable, right? Apart from that, you could put anything else as a value. It does not matter. An array does not have that requirement. An array, you could have anything in there. So that's the definition of a generic. Ability to work with any type with the restriction that you provide, if there's a restriction, right? So that allows us to do sets. A set is a generic. That allows us to have arrays. An array is a generic. I could put an int type in an array. I could put a bool in an array. My own type I could put in an array. So it really doesn't care what type you put in there. Okay, so that's a generic type. Great. So moving on, we will go through a playgrounds example of how we could make generics help us and how we could make generics be reusable in our code. In the same code that we write, how can we use generics to make our code more reusable? Or instead of writing 5 functions and only change the body of the function or the function signature, how can we have one function that takes any type? We'll do that using generics, right? With that example that Apple uses there, this is a very good example. Swap to integers, right? So let's go over to Playgrounds and we'll actually start coding out and see what that looks like. And why is it important to know and knowing how to use generics. So we have a Playgrounds here. It's not a project, it's a Playgrounds. Swift Playgrounds. What's that? It's been a long time since Playgrounds. Keep in mind that throughout your projects, by the way, if you have, for example, we were working with our horoscope project, right? You want to work with dates. You could go to Playgrounds and test it out. So Playgrounds is your friend. Like the name says, Playgrounds. You could test code there. So don't feel like it has to be some structure you need to go into for Playgrounds. Playgrounds could also render views, right? I could create a view here in Playgrounds. I could tap on a view. I could do a lot of things with Playgrounds. So Playgrounds is awesome when it works, right? Yeah, let me hold my breath here. Okay, so let's write a function called swap to integers. So we started by writing some function called swap to integers. Basically, what that function will do the function is going to take in two parameters, type integers, and it will swap them. Okay? So that's what the function does. Our function signature looks something like this. So we have int1 of type int and int2 of type int. Great. Doesn't return anything. We'll take a look, while writing that function, we'll take a look at what's known as in-out functions. So that particular function is known as an in-out function. We'll be using or introducing a new keyword called in-out. We held off talking about in-out earlier in Unit 1 because functions already was a new topic to beginning developers, and putting on in-out there, like why do I need that in-out, right? So today we'll see why we use that in-out. If ever you get into an interview question and the interviewer says, write a function that does something in place. If the interviewer tells you, write a function that does some computation in place, basically what that means is the function does not return a value. The function manipulates some variable outside of the function. It does it in place, right? So anytime you hear in place, think of in-out function. The in-out function, what does it do? It will change a variable outside of its scope, okay? It will change the variable outside of the scope. So if I have my variable outside of my function here, I have a variable, I'll call it num1. Num1, give it some value, and num2, give it some value. Those are two values. With what we know so far, I cannot change that value inside my function, correct? Right? If I go in here, I cannot change my num1 and num2. I have to return a value and assign it to num1 and num2, right? With what we know now, that's not possible. But with an in-out function, I could change num1 and num2, right? So it's as if swap to ints is pointing back, like it's physically pointing back to num1 and num2 and saying, hey, I want to update you. I could update you whenever I want because it has a reference. It now has a reference to num1 and num2, right? So let's see what that looks like. So the code and the syntax for this looks like this. In-out and in-out right before the type. Right before the type int, you put the keyword in-out. In-out specifies I am able to change those variables outside the function, okay? Any questions about the syntax? All right, so in-out functions allow us to change variables outside the scope of a function. Okay. I'm sorry? Yes, which is big, right? If that's your intention, that's what you do, right? As opposed to returning some value, assigning it to num1, right? Now that's a copy, but in-out is no longer a copy, it's a reference. We'll see, syntax we haven't seen yet too, we'll see how we have a reference to the variable, right? In other languages like C++ and Java, where there's like pointers everywhere, right? It's more explicit, like what's happening. But here in Swift, Swift is a modern language. Swift really tries to hide the foundation, or it tries to encapsulate the deeper parts of programming to us as developers. It tries to keep it as readable as possible so that anybody, it's easier for us to pick up that language, right? A language like C++ or Java or even C, forget about it. C, really, you have to get deep down and see pointer arithmetic. There's a lot happening there. But Swift really tries to keep the pointer arithmetic things away from us as developers, right? You really have to get down and say, oh, I want this function to be in-out explicitly. I can't just say pointer to something, right? So it's a higher level language than a C++ or C, okay? Higher level, easier to read. Everybody with me? Higher level, easier to read. That's why Swift has been adopted way faster than Objective-C, okay?
It makes it easier to read, but it also makes it a bit difficult to understand. Like, I just don't get it really well
In a sense, because the encapsulation is hidden from you, correct? Right. I understand that because I do get that what Emily says with Objective-C, for example. Like when we teach you guys Objective-C, some people say, oh, I understand object-oriented programming better now because I understand that there's a header file that has the interface of what the functions looks like, and there's an implementation file. Like I better understand object-oriented programming, but in Swift you have one file, right? So understanding object-oriented programming becomes more abstract, if that makes sense. But we'll get there. Okay, cool. So we have swap to int. What does that do? Again, it will swap. So num1, at the end of the day, we want num1 to have the value 13, and we want num2 to have the value 4. Okay? That's the objective of the function. So the function will have references to both those values. We'll write some logic in our function body, and it will swap those two values. Okay? So we'll start off in our function body with a constant. We'll call it temp, temporary. We'll capture one of the values. Doesn't matter what value you capture, but you need to capture one of the values. If I do not store the value of integer 1, when I write this line of code, I'll lose the value of integer 1. Do we agree? Do we agree with that? That's very important, right? Yes, there's a function in Swift called swap, but your interviewer might tell you, can you swap two values without using the built-in function swap? Right? At that point, you'll be comfortable, you'll say, yes, I know how to do it, as opposed to like, ooh, I don't know, like, can I just use, why can't I, right? So being comfortable with writing things outside of built-in functions is important. So here we saved, we could say here, we saved the value of int1 to avoid overriding it. Because we all agree, if we do not save that value and we say int1 now has value of int2, what currently would the value be? If I was to comment this out, they would be the same, correct? Right? So you need to save that value. So we saved int1. Now we could go ahead and override it with the int2's value. And next up, what are we going to do? We'll say int2. What does int2 equal to? Temp. Very good. So at this point, we have swapped those two values. Okay? So we'll continue on. We'll call our function. We'll write in some print statements here. I'll say print statement values of ints before swap is, and here we'll simply use string interpolation. We'll say int1 and we'll say int2. Those are the values before. Num1 and num2. Those were the values before. And we'll go ahead, we'll call our function. Our function is called swap to ints. Let's take a pause here and see what's going on. So now we have syntax we haven't seen before. We have our function's signature. It says swap to ints, returns void, doesn't return anything. But now we have this ampersand that we haven't seen yet, right? This ampersand here denotes that the function has a reference back to those variables. Everybody with me? The ampersand before the integer, do we see that? Okay? It says that the function has a reference to those variables. It needs to be a variable in order for it to be changed. So I need on 11.9 on the ampersand. You see the ampersand right before int?
It's the and sign.
The and sign, ampersand, and sign, right? And sign, we see it? Right before int, the two int variables, we have an and sign or ampersand sign. It denotes that, it says that the function has the ability to change the variable values. Okay? That function, swap to ints, has the ability to change those two variables. That's what the ampersand does. And how does the ampersand come there? It comes because we said the function is in-out. Explicitly, we mark the function as in-out. That's why we have the two ampersands. Everybody with me? Questions about that?
So like, is the percent take the place of it out?
Yes. The place or the continuation of the in-out. You define it as in-out, and on the receiving side, when you call it, it shows as not in-out, but it shows as a reference with the and sign.
That's how that
Exactly, exactly. Cool. So it could be one or the other. It could be both. In that case, we want both. So both of them are marked in-out. Any questions before I move on?
Just repeat that in the note, that the function has the ability to change.
Yes, exactly. It has a reference to the variables. So it has the ability, if I have a reference to you, I could change what you have, right? Right? If I have a reference to your bank account, I could do things, yes?
Increase it, please.
Increase.
Increases for me.
Okay. Increase for you might be different to, right? We could increase it, but, all right. Cool, so if I have a reference to my variables here, I could change their values, correct? Correct? Before we move on. Stop me, I don't want to move on if we have questions about this. The function wants to have the ability, the function here, wants to have the ability to change the variables outside of its scope, right? If I do not have the function as in-out, there's no way for me to change num1 and num2, right? As the function stands right now. The only way is to return a value and assign it back to num1 and num2. Do we agree? Right? The next way is to mark your function in-out and have a direct reference to num1 and num2. Right? So anything I do to those variables here affects the values outside. Everybody with me? Anything I do to those two values here, int1, int2, inside of the function, affects what's outside of the function. Why? Because I have a reference directly from this in-out outside to my num1 and num2. Okay? Let's see this. So we have our function here. Function. We call it 2ints, for example. It has int1 and int2. Right? And I have my variables outside here. I have num1 and I have num2. Right? So whatever I do to my int1 in here, whatever I do to int1, so if I say int1 equal to 11 and int2 equal to 20, right? By marking this in-out here, by saying in-out functions, I have a reference directly here. So this guy points to, let me go back here. So I have a reference from int1, it points to this variable. Int2 points to this variable. Everybody sees that? Does everybody see that? So anything I change in the body of the function affects what's outside by marking it in-out, right? Those are the big keywords here. This in-out here, without in-out, there's no way you could reference back to it, okay? All right, any other questions? So let's continue on. So let's finish implementing our swap to ints. So for our first one, we have num1. Second, we have num2. So at this point, we called our function. It's affected the two values already. It's affected the two values. Let's go ahead and print out those values. I could just copy this line. Values of ints after swap. And let's print it out to see the results. So there we go. Do we all see my console at the bottom? Right? So values of ints before swap is 4 and 13. Values of ints after swap is 13 and 4. So the function did its work. It has pointers to the outside variables. It was able to change num1 and num2. So if somebody tell you write a function that does some operation in place. So in place. The play button right here at the bottom in the debug. In place means our function should be an in-out function. Okay, cool, great. So here we saw in-out functions before we even spoke about generics, right? So that's good. Cool. So now we want to write a next function that swaps two doubles, for example. At this point, are we going to write a next function that swaps two doubles? How would we refactor it?
Instead of it being int one and int two, I put double one, double two, and then instead of being double.
So you change it from int to double, correct?
Yeah.
But what if I still want to have that int? What if I still wanted to take ints?
You typecast it. Or
It will still only work with one, regardless of what you do there, right? So the int works with ints because ints and doubles don't work together, right? So I would have multiple functions to write, right? Somebody comes with something else, they say, oh, I want to swap two strings, right? So very similar. If somebody says, okay, I want to continue on and I want to say swap two strings, for example, right? Somebody else comes with their own type of object. They say, okay, let's swap two fellows, right? Because you have a fellow object. You want to swap two fellows, right? You see where we're going with that? How many functions are we going to write? One for each until at some point people are saying, is there another better way to do this? Right? Like, there should be a way. Like, programming has been around for so long. Like, couldn't we design something different? We've done that. It's called generics, right? So with generics, we could write one function that takes in any of the types that we want, right? We could write one function that takes a double, a function that takes a string, same function takes a string, any type, our own custom type. So we'll go ahead and do that. We'll write some function, we'll call it swap to items, for example, that does exactly that, or swap to values. Okay, so we won't do swap to strings or swap to fellows. We'll go ahead and we'll create a generic function. Okay. We start off with the func keyword, nothing different here. We give it a name. We'll call it swap to values. Okay? We've used angle brackets before. Where have we used angle brackets? Result type, right? Result type, we use angle brackets. Where else did we see angle brackets? Set, right? So the angle brackets we've used so far, those are generic angle brackets, and we'll use them here. So we'll use angle brackets. We'll specify some type. We could call it T. We could call it E. We could call it whatever we want to call it. Convention uses T for type, some type. But don't think that T is tied in with anything. Everybody, right? Same way I could have any variable name. I could have any generic variable name. Here we use T for type. I could also say element. We see that sometimes here. Right? Those are conventions, but we'll stick with T. T is fine for now. So my type is T. It takes in any type. So that is already starting off a generic function. A generic function, after the name of the function, you put in angle bracket, T or whatever you want to use, U, V, whatever, close angle bracket. Continue on. We will start off, we'll say value 1 is of type T, and value 2 is of type T. Okay? At this point, the function signature is pretty good. The compiler is happy. We could continue on.
But shouldn't we use in-out?
Yes, we will. Very good observation there. See that? In-out. We'll use in-out because we still want to do the same logic we did earlier. Very good. Question, yes?
Can I use
Yes, you can. I could have a next argument here, whatever, random, which is of type bool. Same as functions, they take in multiple arguments. Good question. Okay, cool. So as Julia says, we.
Just one quick question.
Yeah.
I understand we can use any character for in place of T there. Is there any particular reason why we're using T?
T is convention, like T from generics, from the creation of generics in Swift, like T is like the convention you use to specify a generic type T.
Okay.
T for type. Yeah. Uh-huh. Yeah. Very good. But feel free to just use G for Greg. Yeah? Okay, cool. Great. So let's go ahead and mark this in out here. Thank you, Julia. Because we mark it in out. Why are we marking it in out? Why are we marking it in out? David? Why are we marking the function in out? Why did Julia say we need to mark it in out? So we could change the values outside of the function. Remember that, right? It changes, it has a reference. Since it has a reference to the outside variables, it could change their value. Everybody? Okay. Cool. So it's the same syntax like we had up top. What do we need to type in here? So we have some temp, and our temp could hold any of the values. And we want to change value 1 in this case to what value 2 is. And we'll change value 2 to what value? To temp. Okay, cool. So let's test this out. So let's see. We have some variable. Let's say name 1 equal to. Look at that. Now we're working with strings, right? Name 2. Values of swap is name 1 and name 2. And we'll call our function swap to values. So here you see swap to values. It doesn't know what type it takes yet, right? Value 1 colon and or ampersand T. It doesn't know what type. It does not care. Everybody with me, right? So T here does not care. It could have an int, it could have a bool, it could have a string, doesn't care what type it is. Everybody? Questions about that? Shania? Does it have to be the same type? In that case, it has to be the same type, right? Because we swap it. If we start off with an int, we have to continue with an int. Okay? Good question. So next up, what do we have here? We have name 1 and we have name 2. I'll copy this. This is the place we can copy. This is fine. Values of swap after. Let's see what happens here. So values of swap before is Alex Paul. Values of swap after is Paul Alex. So that works on strings, right? Same thing, it will work on ints, it will work on doubles, it will work on our own custom type, doesn't matter. Everybody with me? So at this point, we've written out a generic function. This here is a generic function. Okay? So instead of writing 6, 7, 8 functions, now I have one function, works with any type. And that type doesn't have any restriction. So it could be anything. It doesn't have a restriction. Very similar to an array. There's no restriction on that type. Yes, sir?
Why do we put the generic value and not any? Or is it?
You mean the type any?
Yeah.
Okay, good question. I was waiting for that one. So Christian says, why don't we just do any here, right? That's your thing?
Yeah.
We're not doing any because any could imply any. Like as somebody was asking for, like in Swift, Swift is a type-safe language. So if I say any, I swap an int with a double.
Oh, so like those two are the same.
Right, exactly. You want to really keep your types generic and type-safe as possible. Because again, we don't have an array of mixed types like JavaScript. Because when you take those values out, if you want to add two of them together, you have to really know, do they match, right?
So it's like it could literally mean anything, but those two things have to be.
Exactly, same type. Very good. Good question, good observation. Yes, sir?
Could I add another generic value, like let's say z, and add a second type to the function?
Yes, you can. You could have multiple types there. With like you could have U, V, T, whatever it is.
So long as
And each is a different type.
so long as they're like respective to their
The outside angle argument.
yeah.
Like it expects, like since we said, hey, expect some type T, we give it a type T. If you have U, for example, it would expect some type U. It knows about it somewhere.
And that's how I can mix like strings into it.
Exactly, exactly. All right, cool. So we spoke about so far objectives of the day. How we doing? We're doing good. Objectives.
So wait, I have a question. So we can't use a num, we can't swap a num and a string and a generic? Because I'm trying to do it now and it says cannot convert value into a string to expect.
Look at our line here on line 13. Line 13,
Uh-huh.
right? Do you agree that you cannot assign an int to a double?
Yeah,
You agree you cannot, right?
yeah.
So very similar. They need to be the same type in order to assign one to the other.
So would I typecast it as a zero?
You would have both of them needs to be the same type. In our example here,
Even if it's generic?
even if it's generic, it's expecting the same type. It's not any.
What is the generic doing?
The generic is saying if you specify, you start off with a string,
Uh-huh.
the other type better be a string. Because we have only one type here. T is one variable, one type.
Okay, so how would I make it different types? Is it possible to do different types?
You could do, if you want to do a different swap, that's your question? You want to do a different swap?
And let's say I wanted to swap my name with a number. Like let's say I wanted to swap that. And then,
You want to swap your name with another name?
well, I don't know.
With a number, you cannot swap a string with an int.
I understand, but that's what I thought that's
The generic here still works with the same types.
okay.
Any type,
So
but
there's no way at all.
exactly.
To, okay.
Let's go back to array, for example. If I start off my array, Tiffany, and the class, right? If I start off with some array, and I say my array, I won't even type annotated. If I say my array is 4, 5, 7, 0, an array is a generic type, agree? But now, can I do this? Can I say, let me change that to a variable. Can I say array dot append whatever fellow, for example? Is that valid?
No, but what if we made an array that was the type any?
Then that would work.
Okay, so then.
Any and generic is different.
Oh.
Okay? So if I say I have an array of type any here, those are good questions here. So if I have an array of type any, I could put in,
You can just say append instead of.
yeah, exactly. I could put in true, I could put in 90 point whatever, and here, this would be fine. Do we all catch that? Do we all catch? That's a very important question, right? Any is any type, right? Doesn't matter, there's no type safety there. So with any, there's no type safety. Everybody? With any, there is, let's write that down, please.
So then what does the T, what does that function, what's the difference between doing that and doing multiple functions?
This will work, if you want to swap two values, here we want to swap two values of the same type,
Right.
right? You agree?
Yeah.
Okay. If I want to swap two integers, do you agree that this function works?
Yeah.
If I want to swap two strings, do you agree that this function works?
Okay, that's what you're saying. So in that, when it's a type, you just put you don't have to specify whether it's an int or a string.
Exactly. That's the generic part of it, right? But if you want to work with like any type, meaning it doesn't matter a string, integer, in the same thing,
Angle bracket, any?
it would be any. It would just be any. Like instead of no angle bracket needed, your type would just be any.
Okay.
Okay? But that breaks like the whole Swift type safety mechanism because now you're not type safe anymore.
Okay.
Right? Because you could swap basically what you're saying an int with a double, but you have to figure out what it is.
Right.
Okay? And that would still crash because the compiler would tell you cannot assign integer to double.
Got you. Thank you.
No, that's good. Those are good questions there. We're writing some notes, right? So any is not type safe. What do we mean when we say type safe? Swift is a type safe language. What do we mean when we say type safe? Mel? Exactly. So everybody heard what Mel said. If it's type safe, strings works with strings. That's it. Doubles work with doubles. The language makes sure that the type is the same type. You're working with the same type. That's type safe. JavaScript is not type safe. I could dump in anything into a JavaScript object. Does not care. TypeScript is different, right? Swift is very type safe. If I start off with a string, I cannot change it to an integer like Python, right? In Python, you could start with some value. You could just say num equal 5. Then here I could say num equal, to some string. Then here later I could say num is true. That's valid in Python. In Swift, look at that. Red everywhere. Painting the screen red. Not valid. Everybody with me, right?
How does that work in JavaScript?
Well, the language designers design it that way for the web, right? But that's valid Python code, but not Swift code. Okay, so here we say any is not type safe. Generic enforces type safety. Awesome. Cool. So let us go up and I'll come right back. Objectives so far, we've done in-out functions. We've introduced generics. We've used generics from, again, Unit 1, but today we actually created our own generic function. So we created a generic function. Next, let's go create a stack. Right? We'll create a stack using a generic. So our stack will be able to work with any type. We could have a stack of plates. We could have a stack of ints. So we'll talk about what a stack is, and we'll design a stack implementation. Okay? Can you see? Should I blow it up?
If you can just build it or make it white instead of gray,
White?
white would be good because it'll be able to. You can leave it out,
Yes?
that is wonderful.
Yes? No? Class?
That's nice.
No.
All right. Come closer. Okay, so cool. Let us move over to the lesson before we actually implement what the stack is. Let's go to the lesson to talk about stacks. What is a stack? Go to the lesson for today, and let's overview what a stack is. We've used stacks. Anybody want to tell me where you've used stacks in iOS? There's a structure that's basically a stack. An array is a stack, right? Like you append to it. That's very good. Where else have we used stacks in UI? View controllers, right? The view controller lives on the navigation controller stack. Very good. So those are examples of stacks in iOS. In real life, where have you used stacks? Or where have you seen stacks? Or what do you stack? Plates, right? You stack of plates, stack of pancakes that Jamie made for us, right? So all those are stacks. Here we have a stack of plates, right? Look at that. Right? So we have stacks all around us. Even when in Xcode you call a function, that function goes onto what's known as a call stack. You call a function, hello world, whatever, it goes onto the stack, the call stack. Right? As you call functions, they go into the stack, they get popped from the stack, same as like you have a view controller with a navigation controller. So today we'll start the first time that we create our own data structure, right? So a stack is known as an abstract data type. Why abstract? Because we're the ones implementing it based on what we want. It's abstract, right? You make it what you want it to be. So we'll create this abstract data type of stack. We'll call it stack. It is a stack. And throughout computer science, whether it be Java, JavaScript, whatever it is, computer science, there's stacks everywhere in every language. So the implementations or the jargon, the terminology, they're all the same. How do you add something onto a stack? Using what you know from navigation controller, how would I add a plate onto the stack? Push, right? Very good. So I'd push a plate onto the stack. How would I remove a pancake from the stack? Pop. Look at that. Are we done? I think we're done, right? We're done with the class today. Okay, so you pop something from the stack, remove, right? So remove is to pop, add is to push. Yes? Those are the two functions that we need to implement in our stack implementation. There's other implementations. Some people use peek, like let's see what's at the top of the stack. Some other people use top, like what's at the top of the stack. Okay? There's also functions you could write, how many items do you have in the stack? Give me the count. Okay? Today we'll implement a basic stack using an array. In the following weeks, we'll come back to stacks and we'll create a stack using what's known as a linked list. Okay? But for today, we are using an array to create our stack. Okay? Yes? So there's functionalities. We know push to add. We know pop to remove. Okay? Very good. So this is the diagram. This is what it looks like. So to push is to add. To pop is to remove. And we saw peek here. In some implementations, you'll see top, like what's at the top of the thing, like you see top here. We have no bottom for now, but if you need some sort of bottom, you could put a bottom, like what's the last thing at the stack, or the first thing. That takes us into how do we add and remove, like what's that structure look like? So in a stack, what's the first item that comes off the top? When I remove something from a pancake, which one am I removing first? Is it the bottom? What am I removing? The top, right? Look at that. Somebody's been reading ahead. So the last in, first out here, last thing that went in, or the last pancake that Jamie served at the top here, is the first one that Mr. Benvenido is going to eat, right? Very good. So that's the data structure. Last in, first out. That's like a beautiful thing for the movie line, right? But that's not a movie line. That would be awesome, right? But that's like a different topic. That's queues. We'll get there, but that's queues. I know some people do use a stack when they go to the movie theater, but in real life, we use a queue. But here, it's a stack of plates, a stack of pancakes, right? We're not grabbing the pancake from the middle. We're grabbing the pancake from the top, right? But New Yorkers, they tend to grab like newspapers from the middle, right? You never take the top one, right? Do you guys do that?
Yes.
I do that. I don't know why. Yeah. Oh, you take the top, Emily. You're very nice. You just don't buy papers. Yeah. Okay. Save the trees, right? But we tend to take magazines from the middle, the bottom, right? It's just like a New Yorker thing. I don't know. But yeah, in reality, you take it from the top here. Great. So we know last in, first out. Remember that. A stack is last in, first out. When we come to a queue, we'll see what that looks like. The methods we'll be implementing is push, add, pop, remove, peek. What is at the top of the stack? A useful function, is it empty? Is this stack empty? Can I pop from it? You need to see if it's empty before you remove. If you remove from an empty stack, boom, your app crashes if you don't check first. So that's very important. Performances. How do I access? What's the speed? What's the runtime complexity? I need to hang the, we have a chart there, a big old chart that will hang right where the constants and variables are. I don't think we need constants and variables anymore, right? We above that, right? So we're gonna go, exactly. We're gonna go over to the big old notation sheet. The what? Slow my roll there. We'll go over to the big old cheat sheet this. We're gonna have a chart very similar to that one, where we hang on top the board there, so that we start knowing what temp complexities are. And we'll have a chart here where you look at a stack and it tells you what is the runtime of accessing something in the stack, right? What is the runtime of searching something in the stack? If you have to search in a stack, you have to go through the entire stack, right? If you're inserting something in the stack, you just insert at the top, okay? You remove the same thing, you pop from the top. The runtime is constant. The runtime of inserting is constant. Why? You just put it at the top, append. That's it, you're done. Okay? So we'll have the big old chart back up here. Let me select this out. I know we've had selected out many times, but this is unit 4. We really need to start doing our DSA, knowing our runtimes. This is the time where we really have to start sharpening up and knowing what runtimes are. So I will start this out. Please, again, bookmark it. But the chart will be in the classroom as we go forward. Great. So accessing an element, linear, right? I need to go through the whole stack to know what element I'm looking for. Same as finding an element, I can't just find an element at the top. I have to go through the entire stack. If I go through the entire stack, that means I go through every pancake to see which one has strawberries. Right? Jimmy said one of them has strawberries. I have to go through each one. Unless I'm David Blaine, then I could just know. Who knows David Blaine? Anybody?
I do.
Okay. Awesome. Did you see him in Times Square? Not Times Square, Lincoln Square?
Was that where he did the ice today?
The water, yes. And he almost drowned, right? Okay. David Blaine. Cool. Insert an element, we push. If you push, that's a constant time operation. I push onto the stack, it's constant time. I don't have to go through anything else. I just add that plate at the top. Constant. I'm not going through any other element. To delete an element, same thing. I pop from the stack, that's constant. Awesome. We spoke about some use cases already, and we said the implementation we'll be doing is using an array. So our main data structure for our stack will be an array. The array will hold all the plates. The array will hold all the pancakes or whatever it is. And that type will be a generic type. Because we could have a stack of pancakes. We could have a stack of whatever we want. Everybody with me? So it all ties up together. Generics is a big part of understanding abstract data structures or implementing your own abstract data types. Yes? Yeah, we just pop. The functionality for that data structure is pop. That's it. There's no indexing into the stack. Very good. Okay, so we are good. Let's go implement it. Any questions before we move on about the functionality of a stack? Yes? Pick is like, can I see what's at the top? Like a pick, you know, like you want to pick through a window. I'm sorry? Yeah. Exactly. I'm sorry? In implementations of stacks, you don't see picking at the bottom, but yes, in reality, you can do your own bottom because you know what's at the bottom. But with our implementation, we don't have a bottom. We only have a top. Because we remove from the top, we add from the top. We don't do any functions from the bottom. Cool? Good. Great. So we'll keep this here, and we'll implement a stack, a generic stack, using an array. Okay? We'll start off with a struct. We'll call it stack. If I was to create, for example, I'll just put it right here. If I was to create an int stack that only works with integers, it would look something like this. Private var, let's call it elements, and we would have an array of integers like this. But this would only work with integers. Do we agree? This stack would only work with integers because the elements here is an array of ints. But that's not what we want. We want our stack to work with any type. So to make our stack work with any type, we go to generics. We start off with our type name. Similar to our function, we need to have angle brackets specifying some variable or character t or element, whatever we want here. So I have an angle bracket after the name of my type. So here, this is a generic type. Before we made a generic function, this here is a generic type. Our generic type is a stack of type T. So now we specify there's a type T. We could use T anywhere in our body of our struct here. So I could say my private var of elements equal to some array of type T, right? Works with any type. And back to Tiffany's point of clarification, when we say works with any type, if you start off with an int stack, you have to continue with an int stack, everybody, right? If I start off with my stack being a string type, it needs to continue being a string type. Very similar to our arrays. I started with an int array, I have to continue with an int array. Midway in, I can be like, oh, I changed my mind. Doesn't work that way. Cool? All right, so what's the functionality? Can somebody tell me one of the functionalities we have in a stack? What can we do? How can we add to it? Push. So let's write a function push. Will our function take in any arguments? It should, right? So it should take some sort of item or some value. We'll just call it item here. Item is of type T. Again, from now on, if we're in that generic type, everything is of type T, right? So we put some item, and that item, we simply say append, well, elements dot append. And now look, the function is expecting some type T. So we put in item is of type T. It's happy. Not really. We have an error here. Remember when we said back in Unit 2, if we have a struct and you change in the underlying properties of the struct, you have to mark the function what? Mutating, right? I have to mark that function mutating as according to what Bienvenido said here. Because now it's a copy, I need to explicitly say, yes, I understand, I am changing my copy's property. So I need to explicitly mark or use the compiler and fix it here. But we'll simply say mutating in front of my function name, right? If it was a class, I would not have to do that. Because a class, what's the difference between a class and a struct? A class is a reference type, right? So I have access to that reference. I could change whatever I want to change, right? I don't have a copy of anything. Elements. You see the minute I said elements.append, the minute I said elements.append, I'm changing my array, right? So if I comment this out here, if I comment this out, I take this out here, and I'm not doing anything, there's no problem. But the minute I'm trying to change one of my properties on a struct, I need to mark the function that's doing the change, mutating. And we'll mark this function public because we need people outside to access it. Great. So this is good. I'm able to push items onto my stack. What's the next function a stack could do? Pop. Okay, so let's go write the pop out. So pop removes. Pop removes. And here we could return what we removed from the stack with some optional. Why are we marking it as an optional? Right? Christian says there might not be a value there. If there's no value, we simply return nil. Okay. So we want to remove a value from this. Before we remove the value, like I could simply say elements.remove last, for example, like that, and return it. Right? But there might be a possibility it's empty. Before I remove, I want to check, is it empty? We could do peek, but we haven't written a peek yet. But we'll simply use a guard statement to say guard against emptiness. So guard that elements is not empty. Else return what? Nil. Thank you very much. Awesome. So our pop is good. Our pop is happy. We confirm on line 72 that our elements array is not empty by denoting it with the not symbol. The exclamation mark, not. right?
So what we're doing in what we're doing is creating a generic,
Stack that we could use to implement whatever we want to implement.
but that's not an option for like stacks, that's a
What's the question? If that's not an option for... No, what's the question?
No. Continue, please.
Help us there. Somebody else might have the question.
Myself.
Somebody else might have the question. Like,
But I don't know.
okay, come back to us. You understand that at the end of the day, what we're doing is basically implementing what a stack looks like, right? That's the objective of this particular generic there. Okay, so we have a push, we have a pop. Let's go ahead and write. You could do one of two things. We could write an isEmpty function, but that's fine for now. We are good. We'll come back to this. This is enough. Actually, let's just write it. We'll write it. We're writing it right now, just for you, Luba. We're writing it. I was gonna stop, but I saw your eye piercing into. So let's do a pick here. Type pick is some optional here, and we simply return. What are we returning? What are we gonna return?
Boolean.
It's not a Boolean in that case. Boolean would be for isEmpty. Return the last value, right? So we want to return the last value of the element. So elements, thank you, David, return last. Right? And last here is the last element that was added. And the last element that was added, if you flip that array, it's the top of the stack. So if we go back to one.
Put that there or after you've added something? Or does it really not matter?
It doesn't matter. If it's empty, it's just going to return nil. So if we go back to, actually, let's implement it first, and then we will go to the drawing. So for now, we are good. Let's go ahead and test out our stack. Remember, our stack could work with any type. So what type do we want to have here? What type do we have? Anybody? A double?
Double.
Okay. So let's have a type double. So we'll have cohorts. Cohorts is a stack of type double. Great. So cohorts, how do we add to cohorts? Push, very good. So I'll say cohorts.push, and I'll push 1.0. I'll say cohorts dot push, and I'll push 2.0, and so forth. Cohorts. We have 3.0, we have 4.0, 5.0, and we have 6.3. Great. At this point, if I was to say print cohorts.peak, what should be the answer here? What should be the answer? 6.3. So let's go ahead and run it. Great, so we have 6.3 here. It's optional, that's fine for now, but we have our 6.3. Does everybody see the 6.3 printed? Excellent. So let's try our pop feature. So if we pop twice, what would be the value? Cohorts.pop and cohorts.pop. I pop twice, what's my current value if I say print peak? So we run cohorts.peak. What's the value again? 4.0. Very good. Run our playgrounds. Indeed, we get 4.0. Cool? You guys rocked it? So we saw stacks, and this stack, we could have any stack. I could have my own type. I could create like a fellow here. I could create some type, fellow. Fellow has a name. Fellow has a language. And my stack, if I create some fellows, let many here, fellow, language Swift, let Tom equal to fellow, name Tom, language Kotlin. Right, so here I have two fellows. I could create a stack of fellows. I could simply say fellows equal to stack of, bless you, of fellows, like that. And I could simply say fellows dot push and push Tom, and print fellows, and I would get back Tom. If I was to run it. Right? Cool. So today we saw generics, we saw in-out functions, we saw stacks, right? And a stack is a great data structure for solving problems where you want to grab the last item that was added. You want to keep track of that last item that was added to remove it to solve your data structure. Okay? I'll give us one problem to work on. And there's no turning that problem in. It's just giving us practice. We've started working on data structures. So I'll give us one problem to work on. I'll slack it out after lecture, and then work on the problem, work on it together, whiteboard it before you code it out, or sorry, whiteboard it before you go to Xcode, but get in the habit of start working on problems, right? Okay, any questions with what we've done today? Let me just overview what we did. So we did in-out functions. We created this function called swap to ints, and it's able to change the variables outside of the scope of the function via the in-out keyword. So it has a pointer to num1. int2 has a pointer to num2. So whatever int2 value is, it's a reflection of what that num2 value is outside. Next, we introduced generics. With that same function, we created a generic function. That generic function works with any type, but the two types needs to be the same here. For clarification, please, everybody. Right? So if I have a bool, it's working with a bool. If I have an int, it's working with an int. Next, we went on to say the difference between any and a generic. Any, you could have mixed types, basically. Any, you could have mixed types. But if you start off with a generic type and you start saying the array is int, you have to have that entire array be int. We went on to talk about the stack data structure and what it is and how it's used in computer science and Xcode, how we see navigation controller is a stack, how when we call a function, the function itself goes onto some call stack. And next week, when we talk about recursion, we'll really see how a stack plays in with recursion. Because with recursion, I call a function, it goes onto the stack. That function calls itself, goes onto the stack. That function calls itself again, it goes onto the stack. So if there's 10 calls of the function, there's 10 calls on the stack. And as the function is returning, it returns to the previous function, returns until there's no more calls on the stack. And then you get your answer. So we'll introduce recursion with factorial or one of those conventional recursion topics. So recursion is heavy. Read ahead or watch a video. Cool, so we spoke about stacks, we spoke about the implementations of stacks, we showed the functionality of stacks, we coded it out using a struct. And we spoke about why it's mutating, because we are changing the value of elements here, the property. Right? And we tested out our stack structure. Awesome. So I'll slack out the problem and then we'll work on it.
Can you scroll down to the fellows?
Scroll down to the fellows.
They all have to be strings, even though
Strings. What am I talking about? You mean fellow here?
Yeah.
That's just going back to our basic type. It's expecting a string, name is a string.
I know, but I'm saying do they both have to be strings?
No.
The same type.
No. I could say is currently working or something, is employed. No. I could say is employed here, and then here, I could give it a value, is employed. And here I could give the value is employed. Right? Tiffany? Right? It's our basic type. It could have anything there. All right? Cool. So we'll end here. Any other questions before we wrap up? Any other questions about generics, generic functions? Oh, let me show us one thing before I stop here. Thank you for that. Okay, so on Monday, what did we do Monday? User defaults, right? So on Monday, we did user defaults, and we gave us a challenge to go ahead and create other user default properties or whatever, right? We had an image, we had a cell with a unit measurement, correct? We had a cell with a unit measurement that the user wants to keep track of, and we also had access to a default image, correct? And we said, go ahead, expand the user preference class and add more functionality to save the image, correct? Okay, so one of the ways that you could use generics in your own project is if we click on, we all have access to this. Let me slack it out. So if I go over, this talks a little bit about branching. We'll get into branching. Again, that's like, as developers, there's a lot we have to know and learn. One of the things we'll get into in Unit 4 is talking about branching, right? Right now we have one branch, it's master. If I create a repository on GitHub, I have one branch. That tree has one branch. In that particular example here, the project we did on Monday, I created a second branch. I created a second branch because I wanted to go ahead and write some code that does not touch master. I wanted to write code that's away from master. I wrote code and I called the branch generics refactor. So if on, I slacked out the link. We all have it, correct? Do we all have it? If we see, do we see where it says 2 branches here? We see where it says 2 branches? Yes, Luba? Yeah. Tanya? Okay. If I click on the 2 branches, I have 2 branches now. I have a master branch, which is the default branch, and I now have a generics refactor branch. Do we see that? So it's as if you on some train track. That train track only has one track. That train system has only one track, right? So you want to branch off, you want to go to a different track. It's the same, like in your past, you've gone through 10 towns, right? There's no erasing that. You went through 10 towns on your way to whatever, Pennsylvania, for example. But as you branch off, you continue in your commits. The commits I had in Monday's lab, it still exists, but now I have a new branch that will have new commits on it. Okay, we'll talk more about that, but I'm just telling you guys what branching looks like. But why I want to talk about this, if we go to the user preferences, and let me zoom in here. If we go to user preferences, can we see in the back? Can we see in the back? Okay. This is not what I want. 1 second. Branches, refactored branch. This is what I want here. So if I go to user preferences, I think the link on the repo goes directly to this page, correct? The link on the README. So if we take a look at that user preference, what do we notice? If we take a look at the user preferences, what do we notice? Does anything stand out to us? Generics, right? There's use of generics there. There's only 2 functions. One of those functions, right? There's only 2 functions. One function does the saving, the other function does the retrieving, correct? But the app functions with the same to-dos that I gave you. The app saves the unit measurement, and it also saves the default image, right? But I'm using a generic. I don't care if it's a unit measurement, or I don't care if it's a default image, right? This does not care. It works with any type, okay? So that's a good use case for generics. You catch yourself writing 3 functions, you take a step back. How can I make that a generic type? Yes, sir? Yes, we'll get into how you could conform. Like if I'm adding 2 generic types together, I need to tell the type it only works with equatable, for example. right? We'll get into that as we get more into data structures. Because we'll come to some data structure where you want to compare or you want to add, and you'll get a compiler error saying binary operator not allowed on two generic types, T or something like that, and we have to make it equatable or comparable. But we'll come to that. Let's start. I don't want to go ramp up too quick. Cool? But we'll come to that. Very good observation there. So generics you could use right now in your code. You catch yourself writing two functions doing the exact same thing, just getting different types, stop, rewrite it as a generic function. Okay? Cool? Great. Even with your own API clients, some of them you could actually just have a generic type thing, getting something that conforms to codable, and it works with any type. As long as it's codable, you get your model back. It's crazy. Yeah, generics is awesome. All right, so any other questions before we continue? Or stop, sorry, not continue. I see Brendan's eye here. All right, so we'll stop here. Thank you.